come in? I know.
So you think it's good now? Alrighty.
That was last time I opened one. I pulled out the yeah. Wow. For me, I didn't this. I think with all the fog, I was like,
Sorry, I usually show these presentations in the daytime unless those are closed. I probably should close those, but even then, they'll let you go through it, so the screens are pretty by screen, also in dark time, it's much better.
Are you talking to me?
Yeah.
Okay, what?
Seeing this on the night time, but it's actually better than the daytime in the classroom. Even though it goes like it's like these screens, there's like 3 lights you can't try.
Yeah, it was, it did improve drastically. It was like solid over where you didn't even see them before, but it's really hit down.
There's something like
Over there. And, we get people to pull out. I did. I brought my camera. I didn't want to because I used to be one past there. So I'm like, there's no way I'm hopping on there. I brought my camera. But I couldn't also do it. And then I set up this store. I brought my camera. Yeah, so.
And then.
Yeah, exactly. There's a way to use that.
Figure that out.
Where if there's no so
Exciting, I know. Oh, yeah.
I'm gonna have to have some experience because I know I have you know, like, I don't know who's wrong with X farm, but I'm hoping I'll learn some techniques. Okay, good. Yeah, next month. Yeah, I just got my schedule, so I was able to get it. Oh, I have it. I hear it's like like a nice, really nice place for us.
There he is. This is the new. Oh. Well, yeah. Well, just not a class. I heard this one is really good.
I was introducing Stellarium.
Yeah, I really would like to hear that. But now, have you recorded? You know, what have you recorded?
You know, when I was young, I hated videos.
Yes.
Yeah.
I clicked on it.
Yeah.
I'll send you a note or whatever you have.
Yeah, I'll see whatever I have. I was here in my office on the third floor. And I did a store from. It's like 4 side desks. And tools. There are 2 recently copiers. Right across the hall, my hot car gets me out of the station.
And we used to have some sort of I've been to And he goes, he would,
Well, the head is stretched, so.
looking at the map and it was like, so that they make it. Don't tell us. I don't know. I think we talked about that. I was telling you, the was gonna do down.
Okay, it's 7:30 and we're going to get started.
Uh-oh, nobody's gonna be a winner if they're not sitting down.
Okay, 7:30, we're gonna get started. Maybe. All righty, welcome to the March meeting of the Johnson Space Astronomical Society. Our opening slide today, we have some contributions of the lunar eclipse, which happened just last night from Chris and Angela Wells across the top. Those are their pictures. And Andrew Olson sent us a picture down here in the lower left-hand corner. And that just happens to be a fortune cookie fortune I got at the Chinese restaurant that I thought I'd share with you guys. Thought it was kind of funny. All righty. Before we get started, well, here's our agenda for this evening. But before we get started, I'd like to see if there's anyone that this is your first time here. I'd like to ask you what your name is, how you found out about us, and what your interest is in astronomy. Okay, there's two in a row. Let's get the guy right here in the front of you. Yeah.
All right. My name is Zach Powell, and Rifa brought me. We worked together at NASA as interns, and I've always loved astronomy. Always loved looking up at the stars when I was younger. I'm excited to learn more.
Excellent. Your friend took off before we could embarrass her. Oh, is that her? We've been waiting for you. So come on. No, I'm just, okay. So who are you? And
I'm Rifa. I'm a current graduate intern at NASA doing systems engineering. I'll be starting my PhD in the fall in aerospace engineering. We heard about this on our space roundup, and I came a few times last semester when I was on space engineering.
did you say ES5? Like
EX.
E like Edward X-ray?
Yes.
EX5. Very good. And behind you?
My name is Adam Murta. I'm an engineer in the engineering avionics division at NASA, and I've been working for about 17 years or so. I just thought it'd be cool to learn about astronomy, so I found this on the Meetup app, actually. So I haven't joined the society yet, but somebody posted this event was on the Meetup app, so that's why I found it.
What's your name again?
Adam Murta,
And you're an EV2?
EV8.
EV8. And you've been there for 15 years? Wow. I don't know you. I used to be in that group. So anyway, but I quit. So, all right. So anybody else? Right here.
I'm Lenny Oneski. I'm a dear friend of Chris Randall.
Oh.
Here just to see our friend and see what he's got to say.
You think he's going to say something tonight, huh? Excellent. Who's your two friends? Yeah.
I'm Becky Johnson also. A friend of mine had said that Chris was speaking, so we came for his support.
Is that why he's standing over there?
That's what he's saying over there.
Okay. How about this gentleman here?
My name's Larry Corona, also a friend of Chris, and we got lots of latest coming.
So maybe Chris was worried we wouldn't have a big enough crowd tonight. Anybody else first time here? All right, very good. Looks like Chris is really anxious to get going.
It's a long talk.
Yeah, it is. 85 slides, stand by. Okay, so we have email distribution, and I can hardly believe that people are asking me about how to get on the email distribution because I stand up here every single meeting and tell you guys how to do this. Okay, so if you want to get on the email distribution, if you want to get meetings only, send an email to Ron at this address. You want to get on all the emails, send one to David at this email address. And there's little tear off tabs up there. I'm sorry. The tear off tabs are in my box. If you want a tear off tab, let me know. I'll give you one. I forgot to get them out. That's how you get on our email distribution. Is that not clear? Okay. Anyway, speakers. We only got 2 speakers tonight. So mouse pointer, please use this little doodad on here so that people online can see what you're pointing at. Stream mic is in the computer. Auditorium mic's up here. So you got to stand in this general area. Don't go walking off or we can't hear you, especially online. All righty. So the star of our show tonight is Chris Randall. He's going to just stay there for a minute. Now, first, I got to tell you a little bit about Chris before he comes wandering over here. He's going to tell us about observing the sun, question mark, question mark, question mark. I got to tell you a little bit about Chris here. Most of you guys know Chris, but Chris Randall has been interested in astronomy since he was a child. His first telescope was a 700 by 60 Sears refractor he received at Christmas in 1975. He was able to view Halley's Comet January 10th through the 30th, 1986. Chris got big into amateur astronomy during a geology class field trip in 1988. He is able to watch the George Observatory being built at Brazos Bend State Park, and once it opened, jumped in with both feet. Chris bought his real telescope, a 10-inch f6.3 Schmidt-Cassegrain, April 1990, built a 6-inch f6 Dob, September 1992, hand-ground a 12.5-inch mirror, and got an 18-inch f4.3 Dob, July 2008. He has been a member of the JSC since 1993. He was a president from 2011 to 2012, vice president from 2008 to 2010, and established the JSC website and email list server. He has been a member of the Astronomical League since 1990, currently charter member at large, and assisted in validating the Urban Observer program. Chris has volunteered at the George Observatory since 1990, serving as the 36-inch operator and maintainer. He is also a past member of the Fort Bend Astronomy Club, 1990 to 1999. He has his Astronomical League observing awards include Binocular Messier Objects, Lunar Observing, Deep Sky Binocular Observing, Messier Observing, Sunspotters Observing, Double Star Observing, Universe Sampler Observing, and Outreach Award. He has had 2 articles in Houston Chronicle and several blogs entries for the Houston Museum of Natural Science and an Astronomical League's Reflector article titled Crop Circles at the Okie-Tex Star Party. He should do a presentation about that. And not only that, he didn't put this on his list, but Chris also is the guy that saved me from not using chicken wire on my radio telescope. He says, don't use chicken wire, use hardware cloth. And he was absolutely right. And there's this, in fact, Stan just gave me a DVD or something from the Green Bank Observatory, the radio telescope. Those guys tried to use chicken wire too. And the whole thing fell apart and it was a total mess. So you saved us, Chris, on that one, but he didn't put it in his resume there. So Chris is a great guy. Join me in welcoming him.
Okay, before I get started, I'm going to pass these around for y'all to look at them and enjoy them. And when we get done, just leave them on my backpack at the back. Just be careful. This one is a little gnome in here. And you'll see more about it later. Okay. I'm a really bad speaker, so you have to bear with me. I was hoping he'd have this up when he's talking. You see some of my telescopes. That picture on the right there is from one of the LPI star parties that was published in the Chronicle. And you see the George Observatory and the Hack Winery star parties. Okay. How does the sun move across the sky? Everybody knows it moves, right? East to west, right? Actually, we should say, how does it appear to move in the sky? Because the sun doesn't move. So we know it moves east to west. And so that's your first thought, right? Well, we know more than that. So if you look at this thing, I took this out of my upstairs bathroom window. You'll notice the massive issues with the mating of all the slides because double pane windows at angles make it very hard to align pictures. That's sunrises for the fall sunrise of 2022. I can't read without my glasses here. So that's where you see the sun moves back and forth along the horizons from solstices. So that was a little project I did years ago. And then here's another project I use. These are what they call solar graphs. This one here is actually, you'll see a picture of it as a can with a piece of photographic paper in it and a pinhole in the prop. And this one happens to be tilted at 60 degrees to catch it around my observing fixtures because I wanted to document the sky also when I did this project. So what it is there, if you look here, this is north, south, east, and west. And you see here's June 21st. Here's December 21st. So as you can see there, and these little gaps are clouds. So that's the sun burns onto the picture. And then you don't develop it. You basically scan it and then invert the image and process it. So it's an unprocessed film. And then here's the rest of the year. So this is from December 21st to June 20th. This is a different can, so it's a little messed up, and you got a little water intrusion this time. So that's it. So now when you do a project, you want to discuss the sun, you got to know what time it is. So I say, what time is it? Well, your better answer is which time, because time is not a standard. It is, but it isn't. So this picture got turned sideways somehow. But this is a picture of the time zones. It's civil time zones are divided in 15-degree segments on the sky. So 24 hours and divided 15 seconds. So there's 38 time zones total, though, which some of them are 30 and 45 minutes because of politics and stuff. Okay, here's here's the complete list of all the time zones known out there. And you kind of see it's more than 24. Which is kind of interesting. So back to our topic of time, here's my clocks on my wall. They're all different times, yet it's all the right time. So if you look here in the top, this one here is local mean sidereal time. Those of astronomy know that's the right ascension right overhead. Okay, then I have UTC, which is our favorite global standard. And then I have local solar mean time. Or local civil time, and then I have local solar mean time. I have a tide clock and a moon clock. The only hour hands matter on the bottom two. So that's my wall time. And yes, at night they all tick. And they all tick at different rates. So it's kind of interesting. So now more about our topic, because we're asking about the sun, right? We're trying to observe the sun with question marks. So what is an analemma? An analemma per Webster is a plot or graph of a figure 8 of the sun's daily path throughout the year. So because the earth moves, or the sun moves, earth moves, whichever way you want to look at it, is done. But this analemma represents so much more. Here's a picture from the Netherlands. The guy did a really nice job. He actually used some solar film on his camera to take this picture so the sun wasn't blown out, and then he took it off and took a picture and merged all the images together. And you can see the link at the bottom if you want to go find it. I found it originally, and it took me like half a day to figure out where it really came from to get the guy the right credit. So, but many of you have a globe or had a globe and seen the analemma on the globe. And I always wondered what that meant when I was a kid. Didn't have a clue, never understood it. We didn't have internet back then, so trying to figure it out. But the main talk we're going to talk about here is the Astronomical East program, the analemma observing program. This club is not a member of the Astronomy League because we don't have no dues. As a matter of fact, by the way, you back here, you are a member because you showed up. That's how it works here. We don't have dues. That's one of the reasons why I'm a member here for a long time. I am personally a member at large, and he said a charter member at large, and I was a member at large before it was cool. Now a member at large costs more. I still have the old price, which is kind of nice, but I've been there forever. This is a little shot they put on they have a nice Facebook page. So if you really want to get some good information, it comes out almost daily of different things like the eclipse and stuff like that. Little flyers like this for the observing programs, tell you a little bit about it, tell you the programs. But the Astronomy League offers over 75 observing programs with 26 award variants on those programs. Some have multiple awards for the program. You do 1 level, 2 levels, 3 levels. So that's a little flyer. And in the program, this is an outline of the program. The things highlighted in gray, we're not going to talk about it because I didn't do them. So basically here, if you want to know, there's the email, the URLs for right here and right here are the URLs for all the programs, and then just this one. The website's full of all information. Their website's a little convoluted, but
dig around, click the observing programs and start digging. You'll find all the stuff out there. The program was created in 2010 approximately. The first award was in 2011. So in the package here, we're going to talk about constructing an enclosure, which, by the way, those are mine you just passed around. And then we're going to talk about observing, and then we're going to talk about all the different activities to get the award. Now, being an astronomy league, you have to be a member of the league to do their programs and get awards for them. However, their stuff's freely available, and you can do it yourself and then just for sheer enjoyment. They have a lot of good programs out there if you want to do them. Okay, the program, like I said, there must be a member. The program requires you to observe the sun a minimum of 50 points throughout the year. So they don't want you observing it directly. They want it done indirectly, like a pinhole or a gnome shadow, as you saw in the boxes, if you looked at them closely. But what they don't say in the programs, they want you to go past the year. They want you to have overlap because the program manager will ask a question that I wasn't prepared for, but I knew the answer. Then you're going to calculate the stuff. You're going to calculate using only the dimensions of your apparatus and the plot you're going to plot on your plot. And then using math, you're going to calculate all these things: the tilt, your latitude, the equation of time, the Earth's eccentricity, the ovalness of the orbit, the solstices, the equinox, aphelion, and perihelion. They really don't talk about that in the program, but once you plot the graph out, it's kind of obvious where it comes from. Then you're going to show a graph, the equation of time, hour angle versus declination, and the equation of time. So let's start. This program is not a very popular program. I got certificate number 24. And I got that a month ago or 2 months ago. However, if you notice in 2013, there's 2 from the NHAC. And y'all met this, at least one of them. Aaron Clevenson got one that year. So he's somebody we know that's done it. So there. Now to get started, you're going to have to figure out the apparatus you're going to build, because you got to build an apparatus. You got to figure out where you're going to do it. You got to figure out the latitude, longitude, your magnetic variation. That'll be important. To do that, you can use a GPS, which is nice, tells you where you're at, and you can figure out that for latitude and longitude, or you can find it online on maps. The geomagnetic variation, GPS will tell you true north, but you got to do some playing with that. Compasses tell you magnetic north. Well, luckily for here, it's not a big deal. It's not that much of an error. But you can get it from local airport diagrams, or you can get it from this NOAA website right here. And then there's other decorations we hit in here we're not going to talk about. When you're below the Capricorn towards the equator, you got other issues and concerns. And they also have a photographic version where you can use a photograph, but you need 100 points for it, or Southern Hemisphere. So I'm not doing those. So here is a isogram of the magnetic variations. The green line you see there is a 0 north line. That's between here and New Orleans. So if you look at the 2 line, we're right on top of it. So it's right there. So each one of these lines is 2 degrees apart. So this to the left or right is negative, and it's blue here, and positive to the right here. So, and that's from year 2024. The lines do move. Here's a classic example of the lines moving. We're down here, and you notice the polar north in 1950 something. It's come down, and then right now it's here. Here's the physical spin rotation of the Earth. So you can see that's how it's moving. So it's not moving much right now, but that's a thing. That's off that this website down here. There's all kinds of neat stuff out there on that if you really want to get down to it. But if you're looking locally and you don't have the website, you go pull up aviation airport diagrams off a free website. And if you look up here, you'll see this little circle here. That's the magnetic variation. If you notice there's some writing here, it says, can you read it big enough for y'all to read? It says how much it moved, what year it was done, that took the survey, and how much it's moving per year. And that's for Ellington. And this is for Shoals down in Galveston, same thing. This is off some maps. You'll see a magnetic north grid versus true north. And that's just so you know if you see it on some of the drawings, the drawings are kind of drawn differently. But from the NOAA website, my observing location was 1.76 east. And from Ellington, it said 1.9, and it shows after I calculated 0.1 west per year from the 2020 thing. And then Galveston is 1.7. So I used 1.8. So I established my observing time, and back to that thing. How good is your at pointing something with a compass? A degree, half a degree. So, really it's a moot point. So, because the compass, at least mine's marked in degree increments. So the most accuracy you can have is half a degree. So that's done. So once you get down where you're going to have your location, you got to figure out what time you're going to observe at. So what they're looking for here is solar noon. Solar noon is not noon, if you didn't know, because time zones are based on these big chunks of country, 15-degree segments. And our central meridian is 90 here. You see it right there. It's over off of New Orleans. And that's where central time zone is for us. Others are shown there. So what you have to do is you have to figure out how far west, for our case, of the central meridian we are. And that gives us this formula. And it's 60 minutes per 15 degrees. So you figure how many degrees off you are. I'm not going to go into detail on the math. So you figure out how far you're off, and then you do it. So based on that's the thing, and right now I'm using the coordinates of the JSC heliport. And it shows that the observing time will be at 20 minutes after the hour, 21.79 seconds. Well, 20 minutes and 21.79 seconds past the meridian. So central time noon here, the sun will be 20 minutes later, it'll be here. So during daylight savings time, like now it'll be 13:20:22 for solar noon. And during standard time, it'll be 12:20:22. So it's lunchtime or a little later, depending on your lunchtime. So that's how it works. I'm really talking this because if you read the instructions, they're kind of not clear and smooth, so it may take some learning. So then you go in the instructions. Now you got to figure out your apparatus, how big to build your apparatus. So you use this little thing here. I'm not going to go into a lot of details for saving some time, but basically you take your latitude and you figure out how high the sun is up and down. So this would be north. So the sun will be here, so straight overhead. So if the celestial pole's here, you come back 90 degrees, that's the celestial equator. And we know by our math and previous people doing the work, what's the tilt of the earth? 23.5 degrees, thereabouts. So the sun will be 23.5 above and 23.5 below the central, the ecliptic, or the celestial equator, excuse me. So then we figure out how high the sun will be, and with a little math, geometry, you can figure out the angles. So for this location in NASA, the highest the sun will be is 84 degrees above the southern horizon, and the lowest it will be is 37 degrees above the southern horizon. So that's what you need to know. So you take these numbers and you do a little more math. It's pretty simple. It's just, stuff. So you put in your figure here. So you put your sun high angle and your sun low angle, and then you figure out these angles here, 6 degrees. Will give you, and then you can figure out using on the next slide. So figure out the angles, because all the angles of a triangle make 180 degrees, so it makes it easy to figure out your angles and just supplemental angles and things like that. So more math using tangent, and then I put a little note down here in the bottom corner because most people forget this. When you use tangents, sines, and cosines, make sure your calculator's in degrees, not radians, because it makes a difference on your answers. I didn't have this thing, but I want to make sure I brought it out to you because as all the physics classes, I've been thrown into that on my head all these years. But you can figure the tangents, and then you rearranging the formulas basically here. So basically the pinhole height for my apparatus would be 8.18 inches above the surface, and that the winter solstice will be 0.86 from directly underneath that inches to 10.86 inches. You can do it in millimeters if you want to do that, but I'm an inch person. I'm old school. So if the thing is a little longer than 11 inches, 8.5 by 11 paper might not work because I don't want to get close to the edge. So I end up using 11 by 14. So I have margins just to make sure you can get the whole element. So all this calculating doing now is you're going to forget when you do your experiment, but you kind of figure out because you learn how to do it now. You're basically going to do it backwards when you get your experiment. So you got to get your thing so you can get the whole figure 8 on your paper. So if I put 8.5 by 11 in there, it might run off the end of my paper. So, and then here's the instructions from the thing, how to build the thing. That's what they suggested using. They built it with a triple wall cardboard box, and the other guy built a gnome with some plywood and some screws. The main thing is you got to have repeatability so that every day your apparatus is in the exact same spot when you're doing the sun. Key features you need to know about when you set it up is you need to make sure it's perfectly level. Your true north alignment, not magnetic north alignment. So you got to make sure you compensate for that magnetic variation, which we discussed earlier. And then you got to make sure weather protection and portability. So if it's raining or whatever, you can put it up inside. If you look on here, they got little mark. You can't see it in this picture. You got little marks on the concrete. They recommend doing it on a concrete pad so it won't move. And this guy's got little dimples underneath his little set screw. His screws fits in the little dimples on that one. And those are both from the league. I don't have any concrete. I have a pasture. I have gravel. I don't have concrete. The only concrete I have is in the floor of my barn. I can't look at the sun there. So what I did is I put telephone pole, utility poles in the ground. They're 13 inches diameter, stuck in the ground. About 8 feet, so I didn't have to worry about surface dryness. So I thought. But then again, that's my all-sky camera there in the middle. If you see that. So I sunk that. Then they want you to have a drawing of your apparatus. So I use my little CAD program, and that's mine, and it's all the dimensions on it. So I put this angle here for my pinhole at the same angle as our latitude. So you get the best image throughout the whole day. Because you got to remember, the sun's going to come through here. In the summertime, it's going to come through here. On the wintertime, down to here. So that's my apparatus. It's just passed around. So here's what it looked like being built. This right here was my pinhole test. I used a Dr. Pepper can, nice thin metal. And this was my drill bit set. I have a 110 drill bit set. It goes down to number 60. Well, the smallest hole here is a number 60, and it was too big because it only focused at 5 inches. It wouldn't focus at the 8 to 12 inches that I needed to. So I ended up using, that was the number 55 and 60 there were too big. So here's the pinhole final here, and you see the inside of the bracket I just looked at. This is the gnome. You see it cast a shadow. Then over here, I use my pocket transit, which is basic compass, but it's read backwards because it's reading what's coming to you, not what's going away from you. So south and north are backwards on it. And at the top of the pole, I'll put my north-south line on it. And then I put my mount on my thing. I actually have a little weather cover here. It's a thing. And here's where I put my pinhole camera for my solar graph. On my test day, I put it at my normal height is 30 because I like to get the horizons in when I do my little solar graphs to get the horizon on the bottom and the nice arcs above it. Looks like a bell curve. But for this project, it wasn't right, so I had to put on the 60-degree angle so it's pointing more towards the solar equator. And did it there. So now I got my apparatus set up. So now I got to have the time, right? I got to be a precise time every time I take an ob. So let's talk about how to get time signals. Well, number one, you use WWV, our friend here. Let's see if it works. Play. It's not playing. Oh, well, I don't know how to make it play here. Oh, well, I had WWV. As you know, it takes clicks, and you got to concentrate when you listen to that, or you'll mess it up. So if you got to have a specific time and a specific second, so I'm counting clicks, 1, 2, 3, and trying to watch the sun. I'm not going to do that very well. You can watch its clock on your clock and watch it, or you watch your GPS time signal thing. Again, you're trying to watch here and watch watch down here, and listen and pay attention at the same time. So I came up with a brilliant idea. Everybody has a cell phone, right? Cell phones are pretty close to accurate time because they're reset all the time, and they're always on you. So I said, okay, I'll use an alarm. Well, I did a lot of testing to start with, and I found out it takes exactly 1 second from the time the alarm time hits till it starts playing the wave file. So I took a wave file, I recorded a wave file counting down for 17 seconds because I needed, for my particular, actually it was 17, not 20 like at NASA. So I did a thing, 17 seconds. So I started practicing with it, playing. It's like I was always a second off. I didn't understand why. Well, because it took that 1 second, I had to make it start at 60. So mine says counts down, and I watched the GPS clock set it up so that I know I count down, and I'd wait. And when it beeped, I'd push my pen in the paper. So that's how I did it. But there's also, if you look on this thing, if you go to the really interesting stuff, the National Institute of Standards at Time, they have this 80-page booklet that has all kinds of neat stuff about our time standards. It's amazing if you want to have a little reading. These two graphs show how the time signals are sent out over the stuff and what they mean, and when they have blanks and clicks. And it's pretty neat if you actually want to sit down and I've gotten to where I've listened to so many times tracking asteroids and satellites and things that I can tell by listening to sound tones. I can usually tell where I'm at in the clock without actually listening to the time. But that's just a little sidebar to do. Okay, so now my actual thing, I ended up with a number 60 pinhole was what I ended up with. So it's 0.040 inches, and that gave me the best view. I actually wish I went a little smaller because it actually was bright enough. I was afraid it was going to get too dim, but after the year now, I wish I'd gone a little smaller hole. The thing. So on my thing here, if you look at the little drawing, that's the first few things on my sheet. You'll notice that the hole is 0.117 inches in diameter at summertime, and wintertime it's an oblong thing, which is 0.117 by 0.257 inches, so it's a little elongated. So you got to find the center of that. And then the other one, you saw the gnome, which is shadow. So I was doing two of them at once because I want to see the difference. It's a 4.2 millimeter straight pin from sewing. That's the smallest one I had, and I put it into a pencil and at that angle, so that gives me a shadow, and it gives me a 0.151 inch shadow. I find sometimes it's hard to find the center, especially on cloudy days when the clouds are going by, making little shadows on the. It's kind of neat to watch this pin. I wish I'd recorded one of those. You can take your shadow and you watch the clouds go through, and it's pretty nice watching them. So if I didn't, it was kind of cloudy. I could see a curve, but I couldn't see this where to sit the center. So what I did is I developed a spot tool. So if I got any part of the curve, I can make the center point. And I took a mechanical pencil and put a straight pin in it to make it punching, because I used 1/8 inch foam core board as my thing instead of marking with the pencil. Because I tried to experiment, I tried using a pencil, but it smudged and merved and didn't always give me a kind of crisp hole when I marked. So I used the pen, I just punched it down in the center to make a clean hole. So that's what I did. So it made a very nice marking template. Okay, now the requirements are 50 points visually. So we have 52 weeks in the year, right? Great, we'll just do it once a week. Wait, I go out West Texas 2 times a year minimum. Plus I have some appointments, doctor's appointments and things I can't escape. So then there's weather. So 52 is not going to give me 50 points at the end of the year. So plus sometimes you just don't hear your phone go off early enough to get in there to go do your thing. So once a week's not going to work. So excuse me, I got a little note here that says more is better, because once you do the first equation, the rest of it's done by Excel, so you don't do the math but once. So more is not a problem for you. So I recommend 2 to 3 days a week, like Monday, Wednesday, Friday, or Tuesday, Thursday. So like you can go home, like do it at work at lunchtime, have a spot out in your office, go set it up. You just got to make sure you're there available at that time. So I can do it. But near the solstice, don't do it any more than 2 days a week, because as you see on one of my test ones, I was tearing the paper instead of punching holes because they were that close together at the summer solstice. I mean, yeah. So that's why it's a smaller, and you want to do a little less, but they want you to be equally spaced. So I recommend about every 2 to 3 days. But I was stubborn, and I was going to try to do a bunch of different sheets, 2 different objects, and so I wanted to have the full experience of offsets from solar noon, because you can do it up to 3 hours off one side or the other, and we'll get into that a little bit. But I want to do multiple sheets because I wanted to have one good clean one and not have to mess this thing. But I said, okay, 1 day a week is not enough to get it. So I said, okay, I'll do 5 days. Or every 5 days, I'll have a sheet every 5 days. That'll give me plenty of points, plus my vacation and stuff. That's fine. But 2 rows of ride. It's summer solstice. Like I said, the points are on top of each other when you're too close. And then the trips was going to let me in. So the 5 sheets. But I messed up when I started. I ended up with 6. For some reason, I didn't take the 6th sheet out. I took the 7th sheet out, but not the 6th. So I had 2 things. And I can't punch both at the same time, solar noon. So I set up my shadow one to be 30 minutes later. So 30 minutes later, after I do this hole, the pinhole, I went over to the other side and did the shadow. Plus, also on one day a week, I did a one that just did all these different times, the plus and minus 2 hours and plus and minus 1 hour, so that I could see the whole effect. Because I wanted to play with the math and see how it affected the things for this. Because I mean, they made the program with the exception where you can do the sides. I want to know how hard it was and what you had to do. So, but 3 hours went outside my border. So again, I already talked about, I use foam core, and when I punch the hole, I make a little tick mark, and I have a observation number beside it, and I have a spreadsheet that has all the dates and times and everything. So, and any notes I put on it, like if I was late on one or not, and believe it or not, 10 seconds makes a difference. It messes up your ads or math. So I did that and things. So I did a quick Excel sheet with some data from the internet. The site that I used to get the azimuth of the sun, it no longer exists. I couldn't get the name of it, but I took it and put all the data for my location into a thing. I have the 0 mark here, the 30 minutes late, plus and minus 2 hours. So I wanted to see what it would do, which obviously you can see there. These are inches. So you can see how wide the thing gets to be, just to see if I was going to fit in my fixture before I started. Here's a sample of my log sheet. You can see it's quite uncomplicated. The square root's the closest thing. I found a check mark in my fonts. So I used it for saying I got a good job. A dash means I missed it. X means it was cloudy, rainy, or something like that. So you can see there. And important things like solstices I put on there, even though you're supposed to figure them out. Done. You can see I have the day of the year, the point number, and which sheet I used. And here is the sample sheets that I got out of it. It's kind of hard to read. The E sheet there is the one I did have the best view on it, but it only has 47 points on it. So I didn't meet the 50-point requirement. But you can see the other sheets over here is the test pair. You can see how close together they were. It's kind of hard to see, but it's better than what you see on the computer. And then the other 3 other sheets I put on the thing. So then I have the same thing for the shadow, except it's a different time. And you see the shadow's offset. And yes, that is bird poop. And the same thing, it's got the sheets there. So again, it has a little less than 50 points on it. So then I have a play sheet, which you see, I plan to do it like every Monday, but I put an X when I didn't get it until I got them. You see the check marks all throughout here. And one good day, I got to do them all. So, but here's the play sheets. The one on the left is from the pinhole, and the one on the right is the shadow. Because I did that right after I did the other one, so I got the middle one. So that's kind of interesting to see how they tilt and how the figure 8 cross point moves with the offset of the time. So now we've done a whole year of observing. What's next? Well, I made it hard on myself because I didn't get 50 points in one sheet, which I was hoping I'd have 5 sheets with 50 points. So what I did here is I'm gonna have to merge them together to make my thing done. So the first step is you take all those scanners, because I don't have my flatbed scanner anymore. I used to have a nice long flatbed scanner with a transparency adapter, but it died. It was a SCSI from 286 days. But it had really good amazing resolution back then. So I went down to the local print copy shop and scanned them all. Wasn't bad. They have a nice big 11 by 17 scanners there. So I got them all done. Okay. So there's a note again about you got to observe past your start point to make them happy at the thing. But here is my combined one on the left. That's all my days that I did, all photoshopped, all scale them all, put them on top of each other. And if you look up there, you see the thing that makes this, the sun travels this way. Back, you got the summer solstice, the winter solstice. And if you look over here, you got the different months. But what's neat here is here's the annular eclipse here. Look at the gap. I was in West Texas. Here is a big rainstorm. It rained for like almost 2 weeks, so I didn't get you over there. And then the total eclipse is underneath the cross here. You don't really start, it goes from here to here without any points, because you really can't see. But that's pretty good for a simple setup. I was kind of impressed. Then you do the science. It seems harder than it is. But you'll find here, looking here, you're going to measure the height here from here to here, from the surface to this. I use a piece of safety wire, 40,000 safety wire, which is really stiff stainless steel wire. Put it down and clipped it and sanded it till it was the same height as the center of the pinhole. So then I measured it, made it easy. They recommend using a needle and thread and doing it that way. I tried it. The wind was always blowing. I could never get it to sit still. But you want that center point marked. I recommend that if you do it, mark your point at the beginning and the end to make sure there's no change, because I didn't do it at the beginning. I waited at the end. And then you look at your chart here. You're going to measure the distance from here to here and from that point to there, and that will give you your first measurement, summer solstice and winter solstice. And they use the coordinates -h, meaning 0 is the top and -h is the bottom. And they harped on that many times in the booklet. So then you're going to figure out the altitude of the sun. We go back to our old measurements from the previous exercise, and they discuss here. So now we're using instead of tangent to get it, we're using arctangent to find the difference. So you take the distance divided by the distance, the height divided by the distance from the spot, and arctangent, that gives you the angles. Again, don't forget the radians degrees button on your calculator or Excel. So then you take your stuff, and this is two different things of the thing. You got the equator here, the rotation axis, and then here is the sun's where the sun points, and you got your sun coming in here. So the sun comes in parallel here, and since that's your zenith, you see the angle there is the same as this angle. And taking the formulas, I'm not going to go into all the formula details. Y'all can look at the slides or go download the pamphlet for that. But you take those two equations that they created from that, you merge them, and then you get these numbers here. And so what you're basically in rearranging, you get your observer's latitude is equal to 90 minus the summer solstice plus this winter solstice divided by 2. So using that site and the data we got for NASA's observing site, this I recalculated the data there for that just to have a neutral site, is 29.56. That was real easy. You took 2 measurements and a little arctangent, and you get your added latitude based on the position of the sun. That's pretty cool, pretty easy. Took a while, but 6 months, but it's okay. So now then we got to figure out the Earth's tilt. Well, we already got those 2 equations for those 2 angles. Well, now we subtract them instead of add them. So that gives us the tilt of the thing. So basing all the math down, we get the tilt of the axis is a summer solstice minus winter solstice divided by 2. So for the same thing, it's 23.5. That's pretty cool, isn't it? You're doing major science with simple things. Think about how they did it back in the day with sticks and rocks. Okay, so now we digitized everything. So we got it scanned. So now we got to digitize it, because to do the rest of the stuff, we need the position of every point on our thing. So now that's the only time that more points is worse, is having to do it. Well, I tried it with a T-square and a ruler, measuring every point. I did about 10 or 20 points, and I wasn't consistent on my measurements. I don't know why. I'm being very careful, but they were consistently off just a little bit. So I got smart. Since I had a scan, and I know they're all 11 by 17 scans. So I have a Visual CAD base, cheap program that does CAD. I built a 11 by 17 square blocks. I imported the image that was exactly that size in it. So now my scale's right. And I found every point on the thing in CAD, marked a point on every point, and got the coordinates of it. So then I exported all those things from the CAD formula to a XML file, which is basically a text version of all the stuff. Then I extracted all the points out. So then I took all those points and then, backed up. Make sure I'm getting all the points here. And a coordinate system, because CAD uses lower left, 0, 0. And for this purpose, you need to use 0, 0 as the reference point underneath the gnome or the pinhole as the coordinate. So I had to flip my coordinate system. And so you translate it. That's part of the process in the program doing it. So more details. Says when you bring all those things in the thing, the first thing they want you to do is set up these things. They want you to be able to rotate your coordinate system. So if you didn't set up your true north right, say you just put on magnetic north and you want to correct that, you just put in 2 in this formula, and it'll correct all your points for the shift and your box not being perfectly north, south. For right now, we put you don't put a value in this formula in the thing. So you can see here it's x is equal to the original x times cosine. I wonder where the squares came from. of alpha, which is the angle that you're going to change it to, times plus y times the sine, and vice versa. That gives you the thing. So those give you the pre-rotation coordinates into the new rotation coordinates. It's simple math to adjust your tilt of your axis. If you had your paper in wrong or whatever, or scanning errors, if your scan's off, you can do that. Okay, if you're doing it in Excel, Excel gets very nasty very fast. I'm going to talk briefly about it, but they'll be up there. So basically, use the cosine function, but you got to use the radians term in there because Excel thinks everything all the trig functions are in radians. So you got to tell it it's not tell you to make radians out of that number. That's a degree number converted to radians, and that's what that term does. And if y'all didn't know, if you use these dollar signs, like see here, the $R $sign R $9, when you grab something in Excel and pull it down and copy it, if you put the dollar signs in, it will still refer to that first cell. You don't have to copy that angle cell and all through your spreadsheet. You just have to refer back to that cell. I learned that. I didn't know that before. I learned some things in Excel doing this. So now we do the harder parts, calculate the sun's azimuth. Simple formula. Psi is arctan of x versus y on the thing. And then the sun's azimuth is 180 plus that because it's just geometry matching numbers. So that just gives you the number. I'm not going to go in the details of the coordinate rotations. So in Excel, again, here's degrees because this is thinking these angles are going to be radians. So I got to tell I want degrees. So then it gives me degrees and plus 180, and that gives me the sun's azimuth because this thing's going to calculate from the north. So you want it to go from the south. And then you want to think the sun's altitude, which we call theta. Similar thing, except it's h divided by the square root of x squared plus y squared. Same thing, similar formulas, arctan, degrees, and it's pretty simple. I mean, y'all can come back and look at the slides. If y'all want some help, if you're doing this yourself, you can call me and I can help you. So then we take this, we're going to calculate the declination and hour angle. So take those two numbers, this chart, so we're going to compare them all. So the declination of the sun is going to be the sine of the declination of the sun is going to be this, and then the hour angle is going to be the cosine of this. So you can do all your math there, and I'm not going to go into all the math things, but the units for the top one's going to be degrees, and the meridian is going to be hours. So they come in here. So then from the equation, you take h, will be positive, but to determine, it'll always give you this formula will always give you a positive number. It's just a function of the trigonometry. So then you got to use this equation here to tell you what's a plus or a minus. It's a little bit different formula. And then here's the Excel formulas. So they get kind of complicated kind of fast, as you see. So then here's a plot of the declination axis versus hour angle. So I just put it in Excel, took those columns, and said, make me a graph. Beautiful job. Excel is a wonderful tool, and I use an old version, so it'll do almost everything with the old versions as well as the new versions. So you can see that's the path that the sun takes throughout the year. So then the next thing I want you to do is the equation of time. And y'all know the equation of time is the difference between solar time and clock time, civil time. So when it varies plus and minus because the sun wobbles back and forth in the sky. That's what makes our analemma. It also moves up and down. Okay. So then hour of angle, 60 divide this, they'll give you an equation of time. So you take the hour angle and then a simple function down here. I use the date function and you get the stuff, and that will give you the number of days, and then it gives you the angles. Yes, it's very thing. And what you'll notice, here's the plot of it. Here's the plot of my data. Yes, I have the zigzags because I had the multiple sheets and I didn't get them exactly lined up perfect. They were slightly off. I thought it was a minuscule amount, but it was enough to be off a little bit. And this is a drawback line of Excel just because I didn't rearrange the formulas from the way I had it because I started about here. So unwrapped. So you plot it. This gives you your plot. January 1st is day one. So you see here's 0. And then as it goes throughout the year, it goes up and down the equation of time. It's kind of interesting. You've seen those in charts and stuff. And on my clock, I got a copy of it. So then the next thing I want you to figure out is the eccentricity of Earth. So our orbit's not circular. So we know it's slight oval. So we got to figure out that. So to calculate that is they want is the tilt of the Earth's axis. We change the variable here, and then ends the number of days. And because by definition the vernal equinox is a 0 point on our orbit around the sun, that's why they chose the vernal equinox to start this calculation for this eccentricity. So you're going to figure out the angle of the sun after the vernal equinox. So these formulas, and you have these three formulas here because trig functions have asymptotes. So I'll show you a slide here and explain why you have to have these different degree angles here. When you get to this, you got to subtract this. When you get to this, you got to do this. So you want to know the angle of the true sun. So then it's this formula here. Forget the squares on where they came from. It's probably because the font's a different font set. And then the equation of time is the angle of the sun, the vernal equinox, the angle, and then the sun's angle. And then it's times 1440 divided by 361. You're thinking, wait, circle's 360. I thought that when I first thought about it. Then later on I figured out what it was. Sidereal rotation. The angle of the sun varies relative to the stars, not relative to the sun. That's why it's 361. To get back to the same angle. Because we're used to solar rotation, 24 hours is right back to the sun, not to the stars. So when you're determining our orbit, you got to look at stars. So here is a nasty formula, which I'm not going to go into detail. But those of you that need help, that you can come back and look at the video and look at the stuff. I have them all at the end here if you want to see that page. It's got them all written down. So here's a plot of tangents. Here's 0, 2 pi, 90, pi is 180, 3 pi over 2 is 270. So you notice the tangent functions go to infinity and down to infinity. So that's why you have those offsets. When they go across that line, you got to change your numbers so your numbers will come out right. And here's that question asked earlier. Difference in sidereal time versus thing. So if we take here, we start at noon here, the Earth's going to move to here. So we're going to go past 360 here, go 361. And 1440 minutes is a day. So that's how mean versus sidereal. That's why that formula is weird. And he didn't explain that in there. That's why I wanted to mention it. And then, so my equation, my actual data converted to tilt of the Earth only gives me this graph. Notice here it shows minus 10, plus 10, minus 10, plus 10. And that's just the tilt of the Earth equation based on tilt of the Earth. So then they want to insist eccentricity of the orbit. It's basically the difference of those two. So then here's a plot. Ignore the red line here. So here is based on the eccentricity, or by the orbit is this. So that's it. The red line's for the final data. I didn't want to redo the graph that I already copied. So then you got the eccentricity of the Earth. Now I want to. That was the tilt of the Earth, the tilt of the orbit. Now we're going to do the eccentricity. Similar formulas. Start here. The equation. Wait a minute. Sorry. I messed up my formula here, didn't I? No, it's the similar formulas, but you're based on the year, the day of the year versus, I hadn't read this in a few weeks. So this is basically creating your theory of where it should be. And then you're going to have an e-value of trial and error. That's what you're going to have to figure out. So you can see your same numbers, lots of Excel nastiness. So then the theory from experimental, you got to do some of those things. So now you got these graphs. So you have the combined, which is what you got the first time. Then you got the tilt only, and then you got the orbit only. And those are the three that based on my data that I got. It's pretty nice. So all this done in Excel. This is one of my Excel sheets. Just, yes, you can't see the numbers on it, but that's all the data in it, because I had 275 valid points that I got. Remember, the rest of that was clouds and not here out of the 360 days. And then there's the bottom of the sheet. I'm missing about a third of the middle. I have a little graphs for each little segment to do. So that little factor that we didn't talk about first, the alpha factor for tilt, the correction for magnetic, I use these graphs down here to play with that number. And for me, I got a half a degree off of what I actually set it on. So I did pretty good on that. That kind of surprised me. So, and all right. So the eccentricity orbit, you got to do, you basically going to plug a number in. You're gonna guess the eccentricity orbit. The formulas they gave are only good for small numbers of ovalness. Large numbers don't work. So you kind of know what it is already because you're reading the books. So what you're going to do is you're going to start at numbers. So I first did my formula back on that sheet back there. Let me back up here. This little box here is where I put my test number in, and there's the answer I get from the sum of squares error, which is over here. So these take the error from the factual, from the one that data, from the theory, gives me errors. I sum them up and square them up and sum them up and get this number here. And your idea is to minimize that number. Okay. So come over here. So I first, sitting in my thing, I put in 0.1. I got a number. I put in 0.5. I got a number. I put 0.9. So then I figured out where the minimum was. And I split whichever one's about around the minimum. And I did that 2 or 3 times. It took me about an hour a click because I had to write it down and keep track of it. So I said, this is taking too long to play with these numbers. I mean, I could guess and say, I know it's this and play around with that, but I want to do it right, the scientific method. So I wrote myself a macro. Magic. And basically what it is here, I put a macro in here. This macro goes and takes data off that sheet, brings it over here, manipulates it, puts the value back in that sheet, and checks it out. So the first run of the sheet goes through here, and it looks at from 0 to I can't read my number here, 0.2. I said my first samples. So it's going to take that run. It's going to run it through the sheet and put down in this column here all the values from that orange box that you saw earlier. And then it's going to take that, say the minimum of that, and then put that number up here, or right here in the middle. Right here on this line here on the next column. And then it's going to take, since I'm doing decimal points, that was 0.2. So this is going to be 0.02. And I figure 0.02 a little bit on either side. So then I fill this column in based on that. Now, I did run into error because some of these are negative numbers, and that really messes up the thing really bad. So I had to put a thing in here saying if it's less than 0, make it 0. And then it goes back here and does another decimal place, another decimal place, another decimal as it runs through the thing. And it comes to the final answer. So here's it filled out after a run. You can see here. So whatever it figures out the minimum in this column, puts it here. And then the minimum in this column puts it here. And then calculates these values. And then it goes out. So all that's said and done, to run this thing one time, to run through all these values and give you numbers, 4 minutes. You can see my little numbers here, how long it took to run. And so here's the results of each column. And if you notice, I got the little curve. So here's 0 to 0.2, and it took a minimum. And then here's the next one, the next one, next one. And finally, the last one, I did 8 decimal places, which was more than the requirements. So here's my results of my whole table. Okay, my latitude that I came up with was 29.5564233. The actual based on GPS is pretty close. The only difference of 0.005 and some numbers. Tilt, same thing. Look at that. I got off by a minus 0.04 on the tilt. And then the eccentricity, I got so many different values over the internet. They couldn't believe the different numbers of value, but this is the best one I found from the most reputable source. That's the result I got, 0.0156, and they got 0.0167. So 0.001 difference. Mind you, this is a pen, pencil, and stabbing. Then I'm getting these numbers to this precision. I couldn't believe that. Simple stuff. Reminds me of doing a stick and rocks, figuring out where north is as a Boy Scout. So now I found this website here. It says Omni Calculator. So I put in the latitude. I was 0.4 miles off the actual latitude. Think about that. Simple tools in the backyard. It just blew my mind to see that kind of thing. And that's the results I got there. So here I found a published table of these curves on the line. That's the smooth lines. You can see there, and you see my little jagged lines because I didn't get my sheets quite perfectly lined up. There's a little error in there. It's several decimal points small, but it's enough. So you can see the different curve, but look how close they are to the actual values. I scaled the graphs to the same size and merged them. So I submitted my stuff for my award. I got some feedback. I sent him PDFs of my Excel sheets because I didn't want to send him those huge Excel sheets with macros. Because first off, my mail program won't let me send macros. And so I sent PDFs of everything. I PDF'd everything, made a package and sent it to him. First concern he had was significant digits. Because of the size of my pinhole, you can read it there. I'm not going to read it. My pinhole diameter plus the scaling of the scanner, my significant digits are probably off. Plus, I learned some stuff about Excel. It's 14 and 17 decimal places. If you didn't know that, because that's why sometimes your answers don't come out right, because it may only display so many digits, but it's really calculating it 14 and 17 decimal places. So when you say add 1 to something, it may not necessarily be 2. It may be 1.9999999. So I learned that. But my pencil dot, he made some comments that, so I didn't take that into consideration. I should have in all my science classes back in the 80s and 90s. Should have thought of that, but I didn't. I gave him my handwritten notes of all my calculations, all my notes I took for myself when I was doing the project. When I built the boxes and scaling, all the stuff I saw here on the Excel sheet. He couldn't read my writing. He asked how many guesses I made it. Well, I gave him the answers. I put in my little cover letter that I did 3 or 4, and then I used a macro to do the rest. So I had to repeat that to him. And then told me I only need 5 decimal points of eccentricity, but I did it to Excel was doing the work, so I didn't care. He really said I needed to overlap because the last few days were clouds, so I didn't have a full overlap. He asked the question, what would happen if it overlapped? First thoughts are, it's going to be in the same hole, right? Going around the sun. That's everybody's first guess? Well, it's not right. Because how many days are in a year? Exactly, it's 0.24. So it's going to be right beside it. Because a year is and a quarter. So that's why that I knew that. So I had rebutted back to him that would be the case. Plus, I said I have those sample dates that I started before when they were too close together. I could merge those back in and get an overlap of a week. He said, you don't need to do that. I'm glad I didn't, because that would be a pain. Those so close together, finding out where the actual points were. Because actually 2 of them were like touching each other and you couldn't tell. It's like you just shooting the gun ranger shooting a bullseye and somebody goes, you only shot 8 bullets. I said, no, I shot 10. But 2 of them went to the hole I already made. So I was glad I didn't have to deal with those. So he wondered how it affected the analemma. Again, I said it'd be beside the point because the year is not a full year. And then that's what he said he wanted to. But I got my award. I got 24 out of it. So I did that thing. So I did some other research while I was doing the program. And I looked, this is the thing, I'm going to try to do this. This is a pinhole shot of analemmas. The guy built a clock apparatus to rotate every day and has a slit in it for certain times to get this, so the pinhole projection to get the analemma like this. I'm going to try that one day. I just got to get a reliable clock that can run for a year and not get soaking wet and fall apart. So you can see who wrote that. So here is all my Excel functions I used. Write them down real quick or come review them. Save yourself a lot of work figuring them all out. I will recommend that you pay attention to your significant digits and things like that. And like I say, watch Excel because it doesn't display all the characters it's calculating. I learned that for some other stuff, and I had to figure that out and figure out what it was. But that's it. Now, I found this, and I don't know if anybody's bought a Curiosity Box package. They got this little sundial. I've noticed something interesting about it when I was looking for stuff. Notice that this little vein here, and it says, I don't have one. I'd love to have one. I'd love to play with it. But you flip this thing, it has 2 different sides on it, and you flip it between spring or fall, and it automatically calculates the equation of time because the curve is the equation of time. So your shadow is already corrected for the equation of time. If somebody has one of these, I'd love to play with it for a little bit. It's a subscription service, and it happened to be that month. And I wasn't going to subscribe just to get it and have to cancel the subscription because they're not quite cheap. But they've got all kinds of neat little projects and things. But I thought that was amazing. But if somebody knows somebody has one, I'd love to play with it. And then I did a little more research. There's a sundial that I found. It's already got that on it too. Somebody's got it out somewhere else. And then here's a different sundial that does the equation of time. See the figure right there? So it casts a shadow based on the equation of time. Because you ever go with sundial, you know it's always off. And then here's another one. So did we really observe the sun? Anybody? Did I observe the sun at any time during this observation for a year? The answer is no, I did not. Did we observe the earth? No. Yes, we observed the earth because yes, we never looked at the sun. We calculated our latitude. We calculated the tilt of the earth. We calculated equation of time and the orbit. So we observed earth by looking at the sun. Think about that for a second. That's kind of interesting. Anybody have any questions? No? They say, if you want to take this project on, I recommend everybody attempting it to some extent. Not necessarily for Astronomy League and award, but just set you up a pinhole and mark it. Like you have a south-facing porch, send you a little pinhole out the back and mark your porch every day. Or outside your office window, It'd be kind of interesting. You don't have to do exactly noon. You can offset it. You saw the things. It's kind of interesting. Just do it. I mean, if you only do it once a week and you're not doing it for a thing, once a week, you have some gaps in it. But it's kind of neat to think that that's something simple. You can figure out all this stuff like the old timers did back in the days before calculus and satellites and all this neat stuff. It's pretty simple, but it's fun and effective.
I have a question.
Yes, sir.
Were you able to come across, is there a way to calculate like the circumference of the diameter of the Earth?
Not from this, but there's other things you can do to do that.
Yeah, I just didn't have some, I think there's probably a way to use some of that data. I'm not sure. You'd have to get more data to do that.
I think they use the moon and some other planets to do that, to figure out the circumference of the Earth. And also they'd use the well, the tilt with the wells.
Yeah.
Because over here, your shadow went down the well, over here it didn't. And that's more of the circumference. Any other questions?
I may have missed it, but when you're making your observations, say on a weekly basis, you're trying to do a weekly basis, probably the same time every day.
The time is a critical point. Your time has to be exact within a second. 10 seconds off is an issue. Like I say, some of those points I eliminate them in my drawing because they were 10 seconds off and they made a big spike out to the side or the other side. Because you got to remember the sun's moving, full rotation in a day or thereabouts. So a few seconds is, 15 degrees an hour. So a little bit's a lot. And that's the kiddo thing. So, but like if you're having an issue with that, just do it like I did on the ones for the play one that I did. I called it. I came out every day, once a week, and if I couldn't do it on Monday, I did it on Tuesday. I did it Wednesday. If you do that, they really want it consistent. But I say, as long as you get once a week, you're good. They don't want 5 in the summertime and 2 in the winter and nothing in the middle. That's because you got to kind of think. I didn't cover in here is the solstices, equinox, and all that stuff. Let me back up here to the final graph. I didn't really cover that in this talk because it was kind of complicated. But there's something special about every place these lines cross. Look at the dates. And that'll give you a hint on the solstice, equinox, aphelion, perihelion. If you plot the graph out and think about it, you can figure out those answers. I just I knew it was here, and I put the dates in that I got off the internet, and he goes, no, you have to calculate it. And I'd think about it for another 30, 40 minutes. And I just happened to look at my graph and said, well, let me plot those dates on the graph. And I went, oh, this is so obvious, So if you kind of know the dates and plot it here, the intersections, and that'll give you a hint, and that's where those dates come in. Yes, sir.
So the up and down motion is related to the tilt, and the thing that makes the wide and narrow lobes is the
Mm-hmm. Yes.
That has to do with the pirouetting of the.
Yeah, how far around? Because remember, the sun's not the center of our orbit. The sun is at one of the nodes of the ellipse, or close to it.
Can the sundials that have the lobes in the view, does that take out the difference?
Talking about these?
eccentricity, is that what that helps?
This takes care of the equation of time, because remember the NLM is the figure of time. So what you got to do is you got to watch which side of this you're on. If you go back to my way back here, people at home are probably getting mad because I'm flipping slides really fast. Way back. Oop, too far. Yeah. You see here how it goes here? And the equation of time goes to different months. So you know in October, the sun's going to be here. So the shadow's going to be on that side at that time.
Okay.
So based on where it's at on the thing, because the sun's tilt's the sun's gonna end up on the sundial dial based on coming through the analemma. So this doesn't. The sun comes from a different angle to that dial. So depending on which month it is, it comes at a different point. So it's correcting for that.
It helps to take out the eccentricity of
Mm-hmm.
or the wobble, so then you're that much more accurate in time.
Yes, because if you ever look at
Sundial is pretty accurate.
yeah, if you do that, it's very accurate. Because I was always going with sundials and parks and going, my watch says it's this, and this says it's an hour and 45 off. Why is that? Well, also what you got to know is sundials need to be built for the specific point on Earth.
Yeah.
So if you grab one from San Antonio and move it here, it's not going to work. So I thought those were kind of neat when I found those. Those are just something neat that I saw out there. But that little thing there looks so interesting and playful and something to learn with. And I thought that was interesting. And then I found these online at some park. I forgot where that park actually is. But then there's some other ones. So any other questions? Okay, well, that's it.
All righty, so this meeting is actually a little different. We're not going to have a break. We're going to do a couple presentations and we're going to skedaddle. All right, Ron's not here, right? I know a couple of you guys had DVDs. I'm not the DVD library, but if you really don't want to carry them around, we'll put them in the box, I guess. Rick, quickly about the Sky and Telescope magazines.
Every month, we bring 5 old Sky and Telescope magazines in to give away. So there's, how many are left out there? 4. Okay. There's 4 Sky and Telescopes. Take one if you'd like it. We're just trying to get them around. And we just got, I think it was 25 more, something like that. I got a big pile from Doug. So every month we'll bring in 5. So there's 4 up there. So go ahead and grab one.
Okay, just something interesting. You guys might find this interesting. So in November, Jonathan Kistner came here and told us about 3D printing telescopes. You guys remember that talk? Anyway, this fella is actually now going to be taking over the Sky and Telescope Monthly Astronomer's Workbench. So the guy that came here to talk to us in November is now going to be part of the Sky and Telescope staff running that magazine. Meeting after the meeting, after we get done here, we're going to zip up to Mod Pizza, Middlebrook North, Click City Boulevard to the left, and right in front of HEB is Mod Pizza. We'll get together there and talk about astronomy and other related things. You're welcome to come. So David, Star Party News.
All right, let's see, what is it, enter key?
Enter, yeah.
All right, we had one past event, Friday, February 28th at Hack Winery. I've got that summary coming up. March 15th, tomorrow, Saturday at Magnolia Creek Golf Course. I know a few people have extended their RSVPs. I appreciate that. We'll just see how this one rolls. Doug.
I got a question. Have you talked to them about not turning the sprinklers on?
Yeah, good point. I'll fire that email when I get home tonight.
That'd be great if you could talk to them about that. Last time we were there, the sprinklers came on, and even though we weren't right in the fire, the sprinklers, the overspray was still getting on my stuff, and they just need to not do that.
Next step, yeah.
Yeah.
Okay.
And also, I think maybe some people don't know where this is. You want to give them a quick.
I did not do that. I will also do that in an email. But basically, you look up Magnolia Creek Golf Course, it's off of Bay Area Boulevard.
You just keep going out there.
that general direction.
It's a really long way. I think you guys
Yeah.
know where it was, right? Linda? You went out there,
It is in like the southeast part of Friendswood.
Friendswood,
It's actually 96.
Yeah.
what?
96.
Yeah.
Okay.
Go that route. Okay, but that's a good thing. I'll put out the map for
I
it.
appreciate about the sprinklers. That was a no-go on that one.
We had that at that one
Yeah.
on the east side of Pearland, west side of Pearland
We had to
too.
pick up all our stuff and run.
Yeah.
Yeah.
I just had the Dob. Some of you other people had heavier things you had to pick up and move. It's like,
That's
whoops.
no good.
Yeah.
Yeah.
All right. 27th to 30th, a club's trip to the fort. I've got a number of slides on that. I do need people, if you have already emailed me, emails between work and home, I'm turning probably 250 a day. Emails are going like this. If you've already emailed me telling me you're coming, email me again. I need to start putting together a list, remind them about people staying over to Monday. I'll get there when I talk about the fort. And then the other thing is working on that gate code to get that information back from them.
Yeah, they're not leaving the gate, at least last time they did not leave the gate open. You had to use the gate code every time you came in.
Yeah.
Yeah.
One time Connie and I came back and it was locked and we kind of had to sneak around in the car and find out, okay, we can hop that curb and literally drive through the park in order to get back. But that was some time ago.
Okay.
All right. Texas Star Party, April 20th through 27, trip to the X-Bar Ranch. You guys aren't doing X-Bar in conjunction with the fort, are we? No. Okay.
Not really.
All right. Not this time. Hack Winery on June 8th, August 1st, Okie-Tex in September, same hack again on the 28th. I'll put these out to the club, a week, 10 days before it happens. October again, 19th. That one is technically tentative. Previous one is not. These dates are the dates here in March are confirmed. Okie-Tex, El Dorado, and kind of see what's going on. Then November is going to be the Sun and Moon Night at the George. And then November 15th, we're back at Magnolia Creek outside of daylight savings. All right. February 28th, Hack Winery, Chris Randall, Bob and Leslie Eaton, Reed Klotzer. I thank you very much. Work at a few things just had me fried that night. I was just no way I was going to make it. Chris tells me there's some 300 in attendance. No, Chris was not dressed this way. This was actually from the event in January. Chris took the pictures, but failed to do a selfie. So got a picture of Bob and Leslie with their cool scopes, and then Reed with that ever-present Sea Star pulling up a picture of the Horsehead Nebula. So I do thank you for coming out for that. That was really good. All right, let's do a little quick primer of the fort. Why is it important? Why do you want to go? Fort McCavitt, 2025. Here's our latitude. It's up around 2,000 feet, so it's nice and it's going to be nice and dry up there. Where technically is Fort Mac? I was interacting with somebody today who I thought lived in the area and was, just going to swing by. Until I realized, no, he's actually out there. So he emailed me about that. He plans on showing up for the Saturday. But I was concerned that he thought it was like a local Star Party event like Magnolia. And it's like, no, that's not that way. I said, you do realize this is some 360 miles away from Houston. So tucked down here, Pearland. I know some more of you are more down in this area. Head out your way to San Antonio, work your way up past Kerrville, come up to Junction where Ken and Lisa are. You turn up the road. Over here, FM 1674, make your way 23 miles up, and you come up to this road, you make a trip, and then here's Fort McCavitt. This picture was taken aerially when Fort McCavitt was under Texas State Park, not the Historical Commission, which it is now. Back in the day, you'd come around and we've got the ruins and you've got the barracks. People normally stay in the barracks. In the day, I would tent camp back here. I think you can tent camp in back of the ruins, but not in the ruins. I like camping in the ruins back in the day because the ruins provided a nice windbreak. Yeah. This was supplied to me by Kevin from the Texas Historical Commission. They've made some very clear, obvious modifications. They've got the walking paths with the grids laid out a little bit more. Roads are a bit more defined. The RV spaces that are used to be over here are no more. RV spots we used to have them back here. I still have one of the old pictures in there. RVs and only 3 slots with full hookups are back over here. That's kind of a downer because that means you either got to hoof it to go over or a car. Probably walking would be easier, particularly if we have gate code issues. Hopefully we'll get that resolved before this starts. But you've got 3 RV slots back there with full hookups, water, power, and sewer. I do not know the conditions on the power. I don't know if it's 30 amp or 50 amp. I would plan for 30 if that's your flavor. Buicks from the ruins. We would often park out here, chat, talk about astronomy, talk about everything, pass out, take naps, have our scopes over here next to the ruins. In this case, the ruins would act as a windbreak. This is a very dated slide because that's Connie and John. They're back in the day. That is Charlie McLeod. He's now in Montana. So, but still, the idea is you kind of get the feel of what's going on. I think that is probably my rig. Food. Friday night, there's usually a potluck. Thursday night, as I'll describe in the word slides, people will possibly go to Menard for restaurant fare. Be advised, Menard is actually a very, very small town with a very small town mentality. Some of the restaurants only take cash. You hand them a credit card, no bueno. Hardware store. Sometimes we had to go make a trip to the hardware store. Said, "Oh, my dad decided to close because he needed a nap. He might be back at 4." Really? Honestly, I found more. You want bigger stuff, more supply stuff? Go to Junction. Yeah, it's 60 miles away rather than 24, but at least Junction's a little bit bigger. The gang always cooks together. If Fred Miller shows up, stay close. He's always cooking something good. I don't know if he's going this year yet. We usually try to gather for a club picture. What to bring? Always double check the weather, or whatever weather app you prefer. In March, we have had weather in the 70s and 80s, and we've already had it down to 21 degrees in March of 03. They said, "Oh, it's a light freeze," and I had 3 inches of solid water, frozen water in my coffee pot. Check the weather 10 days prior. October can also be nippy. Sleeping bag, clothes appropriate for the weather. Don't bring a fleece bag if it's going to be in the 30s. Hunter suit often works quite well. Be prepared. Come with Google Maps, as you know how to get to Menard and Junction, even San Angelo if you think you have the need. Hard copies are suggested because when I was last there, the only service that was working there was AT&T. Once you got north of I-10, Verizon goes DOA. I don't know if that is still true, but that's there. They've improved that? Okay. As I said, be advised, there's only room for the 3 RVs there. Once those slots are gone, they're gone. Plan ahead, bring all your own meals just in case. For Friday night, bring something to put on a grill. They usually still do that as I understand, as a potluck. If you arrive early enough on Thursday, as I said, a group tends to try to go to Menard to be one of the restaurants. Ice for coolers, you've got 2 options, Menard or Junction. There was a bar that used to, a little shack around the corner that used to supply ice. That apparently went off. Oh, can I go backwards on this? Yes? Okay, I'm sorry, folks. I usually don't like going that. Somebody tell me what the Sam this is. Doug, do you know? It looks like an athletic complex, which would be surprising because I would be surprised at the what? Okay, so it's not an athletic complex or anything like that? Yeah, okay. I saw that and said, "What's that?" That wasn't there when I was last there. I mean, to be perfectly candid, I haven't been there since April of 2011. I'm flirting with October. We'll get there. Where are we? Plan to eat. Ice for coolers. Yeah. Plan what to eat and how you want to work it. If you don't have a camp stove, bring a folding table with an electric skillet. There's usually power out of the barracks. Don't forget the coffee pot. Bring plenty of bottled water, and don't forget your chapstick. 2,000 feet elevation, it can be kind of dry up there. We arrive Thursday, set up, dinner's traditional, then observe. Friday, breakfast, lunch, you're on your own. Dinner's usually that potluck. Saturday, breakfast, lunch, and dinner are totally up to you, how you want to work it. Understand that Saturday night is the public star party. That is our service to the fort. And so people that are going there, I would please ask that you participate. Sunday, you're also on your on your own food-wise. Observing night, Monday, pack up and leave. Any questions or anything, or you want to say, yes, I'm coming, and how many nights? Please tell me please send the email to me and what your preferred accommodations are. You going RV, tent, or do you want a slot in the barracks? I need to inform them at least about a week before what's going on and who needs what. What you will find, I'm assuming our showers are still there. Back in the day, we had the showers we actually contributed money. The club did. Only buzzards, and as I understand, they're still open air, so only buzzards and airplanes with really good cameras can see you. I have showered and looked up and seen the light of the Milky Way. Hot and cold running water is there, bathrooms, and large porta potties because they do reenactments, and they're actually fairly clean for porta potties. Some of the ladies would have come in with this big giant buffo tent type dresses, and they have porta potties that big to accommodate those dresses. Great skies, nice people, chance to get away from it all. That's the whole plan. Cell phone service, you're kind of on your own. What you won't find at Fort McKavett, quite a bit, you do need to be self-sufficient. Nearest town is Menard, 23 miles away. Groceries, ice, amenities, and some passable restaurants. As I said before, some may be cash only, so be prepared for that. Junction is 40, but it's a little bit bigger with a lot more to it. Nearest Walmart, if you're a Walmart addict and have to go there, it's in Brady, 60 miles away. San Angelo is 80 miles away, and it's actually a small city, and I believe that's may glow off to the northwest by northwest area. You get the feeling if you're out in the middle of nowhere, yeah, you're out there for a reason. You're out there to look at the stars. So above all, I want you to have fun. Feel free to email. If you're on the club list, email the club list. I have posted this primer on the webpage if you'd rather have a hard copy. All reservations, you gotta for the moment, you gotta come through me because I'm talking to the port staff. And with that, I admit this discovery does seem to support the asteroid theory. So that's it.
Okie dokie, artichoke. Next month, April 11th here, my early adventures in Celestron with the Celestron origin, Paul Lotz. Where's the bucket?
Yes.
Okay, door prizes. What's for your door prize number? We got some fantastic door prizes tonight. The best door prizes you've ever seen. Alrighty. So let's see. This is going to require glasses. Okay. 5, 2, 7. Last three numbers. 5, 2, 7. Come on down here. Good. All right. Oh, a visitor. That's good. Come on down here. I have a moon map. I have, hold on. Can I show you what else I got? I got the 2024 Sky Almanac. Now, you may think 2024, but it actually doesn't change from year to year. So you can, except for the planets, right? It's pretty much the same. You got that. I have some astronomy socks. Yeah. Does any of these do anything for you?
The socks.
The socks? Okay. The socks are always a hit, right? Thank you. You're welcome. Alrighty. Let's see. Next one. 5, 3, 7. 5, 3, 7. Do we have a 5, 3, 7? Anybody want to admit you're a 5, 3, 7? Who is it? 2 months ago. All right, another new person. That's good. Okay, you. I have STS-98 crew pictures, NASA crew pictures. I have a patent picture about some kind of weird little, I don't know what that thing is.
Okay.
Okay, book about sky lore anthology,
Okay.
and I have the almanac, and I have a moon map.
choice.
Almanac's pretty good. If you want to look at the sky, that's what I would do. You're welcome. Glad you came. All right, one more. We're going to get out of here by 9 o'clock. It's going to make me cry. 534. 534. Another gun. Woo, what a hit. All right, come on down here. I know, isn't it pretty good? 3 new people. Oh, wait a minute. Oh, wait a minute. This one was hiding. I also have a sign that says, warning, objects in the telescope are farther than they appear. I have that. I have a map of Jupiter. I have a map of the moon. I got the STS-98 crew pictures. I got a patent picture. Skylore. What do you like?
I'll take the crew picture, actually.
All right, crew picture. Oh, that's right. You're a NASA guy.
Mhm.
You see what we were doing back in you were probably there during that time, right? Yeah, very good. Okay, that's it. Thanks for coming. See you later. 9 o'clock. Woohoo! We made it. You gave me my